AC resistance. What we're going to look at in this presentation is AC resistance and how it differs from DC resistance. I mean, why is there a difference? How on earth can that be any different between the two? So let's take a look at a really simple example. I got a source there, a resistor, and a few wires that connect the two together. And my question would then be, which voltage source would allow the higher current to flow through the resistor? Would it be 120 volts AC or would it be 120 volts DC? The answer is a little bit odd. The higher current value will actually be the DC circuit. And that's because in a DC circuit, no matter what we put into the DC circuit, as in any component, only the ohms of resistance, as the French say, will oppose the flow of current. While in an AC circuit, we still have that DC ohmic resistance. But in addition to that, we also have these other factors that contribute to the overall restriction of current. And they're listed here. We've got skin effect, eddy current losses, hysteresis, and dielectric. So we're just going to look at each one briefly, and then that will bring us to the point of discussion of impedance and how that would be utilized. So here's another example. All five together result in this AC, or effective resistance. Dielectric losses have to do with the stress that an alternating current has on the insulation. The electrons are forming in or aligning in one direction, then the next very rapidly. And what that does is it leads to stresses on the insulation of the conductor. And this is much more apparent on higher voltage installations. But that stress causes heat loss. And whenever we have heat loss, that means a loss of power and watts. So this leads to a little bit of lessening of the efficiency of the system. We also have something called skin effect. And skin effect is harnessed in different areas because when an AC system is connected to a conductor, the current will want to flow on the furthest exterior edge of the conductor, which is why on many overhead lines, the center is simply steel, not only for strength, but also because very little current will actually flow in the center of the cable. And so that then means that we have less conductive material in order to carry the current. And that again would be an inefficiency and therefore a bit of a loss. Higher frequencies cause stronger skin effect. And at a certain point, you can harness this. For instance, on oil field pipeline systems, very long runs, there is a system that utilizes this. And track with me here, it's kind of weird, but what they do is they take a pipe, think of it as EMT, and they weld it to the product pipe. And then inside the pipe, they put an insulated conductor. Now, the return conductor for this circuit is actually the pipe itself. So kind of bizarre. And what it will do is the current will flow on the inside of the pipe, and that's because it is closest to this current carrying conductor. Kind of a bizarre situation. Effectively, what happens is that there's no shock potential, but there's heat transferred into the product. Bizarre engineering. We have iron losses, which you've obviously been exposed to in level 1, hysteresis and eddy currents. Hysteresis has to do with the magnetic domains of that material, and they are flipping 60 times every second. And if they're flipping 60 times a second, that would then mean that there is friction, and friction then leads to loss. And how do we solve this? Well, you would mix silicone into the steel and it reduces the friction. What about eddy currents? Eddy currents are another type of loss that has to do with the electromagnetism. When we energize a coil, what will inevitably occur is a circulating current within the core. And this again will cause heat. Anytime we have heat loss, it means that we have an inefficiency in the system, and power isn't going to the object that we want. And so again, we can solve this by slicing that core into tiny little sheets and electrically isolating them one from the next. And that would then prevent the eddy currents from developing and circulating, and therefore the loss of electrical power. This is commonly done in transformers and motors. Anything that utilizes magnetism as its chief means of operation will have the core sliced up to reduce the eddy currents. Sometimes we harness eddy currents, and this would be an example of such a product. This is an induction cooktop. And if you were to harness eddy currents, you're simply using a rather large coil of wire. But remember, it's only going to heat a solid metal or ferrous metal object. And so if you want to take it to an extreme, this is what you get. The surface of the actual appliance doesn't heat up at all, but the pan gets extremely hot. So in a DC circuit, only the ohms of resistance will oppose the flow of current. We don't have skin effect, eddy current loss, hysteresis, or dielectric loss. In an AC circuit, we have that DC resistance, but in addition, we have these four, and those are then calculated and represented by these two factors that you've learned about already: inductive reactance and capacitive reactance. We really don't delve further into this discussion between A, B, C, and D and determine exactly how much is skin effect, how much is eddy current, hysteresis, and dielectric. What we do is we group them into these two categories. And so what that means is that when we're looking at the total opposition or the effective AC resistance, we're talking about the impedance, Z. And it's a combination of resistance and reactance. And reactance is then made up of, well, a combination of these two, depending on what we have in the circuit. Our next video, we'll look at how do we calculate these items, because we're going to be using Pythagoras, a little bit of trig, and an introduction to power factor. So we're going to use some of those skills that we looked at previously near the beginning of the course. But hold on, hold the boat. Do not attempt to memorize every single equation. Depending on what learning resource you're working with, you'll find that there are situations where the author will feel that it was best that they give you every single possible equation known to man on this topic and hope that you then noodle your way through the topic with this. Oh my goodness. I mean, if that doesn't scare you, I don't know what would. This is beyond bizarre. This is ridiculous. And so what I would say is, instead of looking at this chart as you might be flipping your way through your binder resource and finding this and saying, oh my goodness, I got to spend a week and memorize every single one of these. Instead, why don't you go on to the next presentation? And what I'm going to try to do is introduce a process that should really simplify what it is that you need to really commit to memory, and what items do we not need to be as aware of. So please, please do not spend hours memorizing all of these bloody formulas. This is probably not the best way to introduce a topic in physics. Just thinking. So we'll work through the application of the equations as they are required. Take a look at that next presentation and see if it's as complicated as what it appeared to be initially on the previous slide. That's all for now. I will talk to you guys again soon.